Hello, my name is Azim Usmanov, and for my final project for CS358, I'll be exploring CuPy, a Python library. So, just as a quick overview of what we've already been learning in class, as you know, CPUs and GPUs are fundamentally different pieces of hardware, optimized for different philosophies of computation. A CPU, as you know, is built for low latency, branch-heavy sequential workloads, whereas a GPU is designed around massive data parallelism. It contains thousands of lightweight cores that can execute the same instruction across several pieces of data. And in terms of Flint's taxonomy, both devices correspond to a single instruction multiple device architecture just because the CPU, practically every modern CPU, as you know, has multiple cores. So this would correspond to the multiple device. And GPUs as well, obviously, we just mentioned they have a ton of cores. So because of this architecture, we know that GPUs can dominate in applications such as fast Fourier transforms, convolutions, matrix multiplications, and essentially anything with high arithmetic intensity and predictable access patterns. And this exploded, as we know, from the generational use of GPUs and AlexNet image classifications, and this is where GPUs really took off, and we could see another use case from them outside of just graphics. So now, the main question: what is CuPy? And before CuPy, it might just be helpful to do a quick recap of what NumPy is and what it does. So as most of you probably know, NumPy is one of the core scientific computing libraries in Python. It gives us n-dimensional arrays, vectorized operations, and efficient implementations of linear algebra, random sampling, and Fourier transforms. And pretty much every field that uses Python, whether it be data science, physics, or machine learning, and various others, most of them, often a large amount of them, rely on NumPy because it lets us operate on arrays all at once instead of writing slow Python loops and operating manually with Python lists, which, as you know, can be pretty inefficient. And because NumPy operations often apply the same computation over large blocks of data, such as arrays, matrices, and higher order matrices, they're naturally very, very parallelizable a lot of the time. However, by default, NumPy runs at the CPU, which, as we know from class, can limit performance for large datasets. CuPy solves this problem by providing essentially a GPU-accelerated version of NumPy. And it's pretty easy to use, as Python, obviously, it abstracts a lot of details for us. It's very readable. And essentially, it's pretty easy. You can just basically replace your NumPy import with a CuPy import, and it operates basically the same way. It has a bunch of similar methods to NumPy. CuPy mirrors almost the entire NumPy and SciPy API. For example, CP or CuPy.fft for Fourier transforms, CP.linalg for matrix operations, CP.random for generating random arrays, and etc. And under the hood, CuPy dispatches these operations to highly optimized NVIDIA CUDA libraries, which we'll talk about some more here. How does CuPy actually work? Now, as I just mentioned, CuPy dispatches these operations to highly specialized NVIDIA CUDA libraries. And from this CUDA, essentially these operations, a CuPy array doesn't actually live in the main memory. It gets sent to the GPU device's memory, and it's allocated through CUDA's own memory allocator. So essentially, when performing operations on CuPy arrays, the data never leaves the GPU unless you're at the end of the operation, in which you would bring it back to the CPU with a get operation or something similar. And when a high-level operation such as FFT is called, since we have methods for these, CuPy would call the highly optimized NVIDIA libraries. For example, FFTs will go through QFFT, linear algebra goes through QBLAS, QBLAS, convolutions use CUDNN, and certain solvers rely on QSolver. And these are the same backends that are used by deep learning frameworks such as PyTorch and TensorFlow when the GPU is available. So as you know, the performance is extremely good. Additionally, CuPy also supports custom GPU kernels for simple element-wise operations. CuPy can just-in-time compile a kernel at runtime using NVRTC, which is CUDA's runtime compiler. And for more control, CuPy exposes a raw kernel API that lets us embed CUDA C or C++ code directly into Python, giving us full low-level control while staying inside the CuPy ecosystem. CuPy also includes some execution optimizations. Certain modules use lazy evaluation to avoid unnecessary synchronization or data transfers, and CuPy supports CUDA streams and events. allowing operations to run asynchronously on the GPU. And essentially, this all boils down to a simple replacement for NumPy that operates on the GPU when it's available, instead of sending everything on the CPU, which allows us to parallelize our dataset and see performances, as we will soon see from my demo. Now, just real quickly talking about the fast Fourier transform, or FFT. Essentially, it's an algorithm that computes the discrete Fourier transform efficiently, which is essentially taking a signal from the time domain and breaking it down into its frequency components. So essentially, from time versus magnitude, we can see the frequency versus magnitude, and using a time as a third axis, which we'll see in the demo. And internally, the fast Fourier transform is composed of a series of butterfly operations, as to speak. Each butterfly combines pairs of complex numbers using predictable arithmetic. Sorry. Just checking the video. It went out on me last time. But yeah, it computes these using predictable arithmetic operations, and these butterflies across a given stage are independent of each other, which creates, because they're independent, it creates huge opportunities for parallelization. And this structure maps perfectly onto the GPUs, almost so perfectly that we can say it's an almost embarrassingly parallel, because each FFT stage can launch thousands of threads that perform identical arithmetic operations on different parts of the array. And the workload is extremely regular, has very little branching, as we mentioned before, entirely arithmetic, which are all the characteristics that we know GPUs can excel at. So the FFT is pretty much, as I said before, it's perfect for a GPU, and I'm about to show you a live demo illustrating this. But essentially, the program that I'm about to show you will take in an audio file using both CPU using the NumPy library and on the GPU using the CuPy library. This will be on my RTX 3050 laptop edition on my Dell XPS. But this audio file will be the array. This will be the data set that both libraries will be analyzing. So the audio will be uploaded and split into frames, and then the fast Fourier transform is computed for each frame to generate the spectrogram. And these operations, they'll be timed to both the CPU and GPU to see whether the GPU will actually improve the performance. And spoiler alert, it does. And also, just as a fun little visual component, I included a real-time visualizer for these audio files that shows the corresponding frequency magnitudes as a song is playing. This part isn't optimized using CUDA. Only the fast Fourier transform, which generates this which will be used to generate this visualizer, is. But here it is. Oh wait. So here's the video. See it? This will be using with a very bass heavy instrumental. As we can see, there's some silence at the start, but we got a good speed up. So we can see the bass comes in, so both frequencies are again a lot higher magnitude. We got a 5 times speed up and 6 times. That's pretty good. As you can see, CuPy is doing its thing. And here's a more extreme example. As I mentioned before, or I didn't mention yet, but you might be wondering, why is the speed up here a lot bigger? And this can be boiled down to essentially, this is a much longer audio clip as some of you might recognize, but this is the full-length instrumental for EXO Tool Life, a song which is about 3 minutes. But essentially, the overhead from moving data from the CPU into the GPU's memory, it has quite a bit of overhead, but this is reduced just because of the length of this audio file is pretty long, so the overhead is pretty minimal compared to the computation saved, or the time saved by computing this on the GPU. And on the other hand, running this benchmark script with the default argument, just a simple 5-second riser, as we can see, because the audio file is pretty short, the speed up we experienced, it's not too great. So, wrapping up, there are a bunch of real-world cases where CuPy can be used. As we saw, obviously having a real-time performant audio visualizer is extremely helpful in programs such as FL Studio or Ableton, where producers need to see their work in real time. Additionally, it can also be used in MRI or CT reconstruction, radar and signal processing pipelines, machine learning data pre-processing and large tensor operations before these are fed into a model, scientific simulations, and essentially any NumPy style workload with strong data parallelization. However, there are some limitations we must keep in mind. Obviously, this requires an NVIDIA CUDA GPU. Actually, I double checked. This is actually incorrect. There are some modules which are being developed to import this to be able to run on AMD GPUs. However, I have not seen anything similar for Apple. So, unfortunately, if a MacBook is all you have, you will be out of luck unless you can remote into some PC or maybe just use Quest. Yeah, as I mentioned before, and as we saw from the demo, the transfer overhead can dominate if the data moves too often or if the data is pretty small. And you also can be limited by your GPU's RAM or VRAM. I didn't run into this. I use pretty short audio files, but this is something to keep in mind. Yeah, final overview. Just a quick recap. CuPy, essentially a replacement for NumPy syntax, but CUDA performance and CUDA operations if you have available hardware. And as we know from class, GPU acceleration gives us major speedups for parallel-friendly workloads, especially the free Fourier transform. It's almost embarrassingly parallel, but it's a perfect example of an algorithm that experiences great benefits from GPU parallelism. And CuPy uses underlying CUDA libraries such as QFFT and all of these. And just as a rule of thumb, you want to keep the data on the GPU as long as possible. And yeah, because of just the easiness of Python, how readable it is, and the minimal changes you need, this is a very good option for programmers or data scientists or machine learning engineers or basically anyone who wants to see who's using NumPy and could benefit from some speed up. But yeah, this is my final project. I hope you enjoyed learning about this as much as I did, and thanks for watching.